We've now developed a tool set to approach the proof of the strong law of large numbers, and those tools are all named after someone whose name starts with K. Well, we're going to continue that trend, but this time it's going to be Kronecker, not Kolmogorov. You see, the tools that we've developed so far, the Kolmogorov convergence criterion in particular, are well adapted to looking at sums of independent random variables. But what we're interested in is a normalized sum of independent random variables. The tools we have would be more adapted to a sum like this, where we normalize xn by n instead of normalizing the sum of the xn by n. It turns out that from a pure real analysis point of view, these two can be compared quite well, and that's Kronecker's lemma that we're about to prove. Let xk be any sequence of real numbers. Actually, the proof we're going to give here works in any normed space. And let bk be a sequence of positive numbers that increases to infinity. If the limit of the sum of xk over bk exists as a real number, then the normalized sum of xk all divided by bn converges to 0. We're going to prove this now, and as we prove it, let's think about this in calculus type terms. Here we have something like an integral of a product of things, and we'd like to pull one of those terms outside the integral, maybe at the expense of integrating the other more. Well, that sounds like integration by parts, and that's actually what we're going to do here, except it's summation by parts. So to make the notation a little easier, let yk denote xk over bk, and let Sn be the sum of the yks. That's the thing we're going to assume has a finite limit, with the desired conclusion that the normalized sum of the xk's by bn actually goes to 0. Also, just for notation's sake, let's define S0, the sum of 0 terms, to be 0, and let's let the limit of Sn, which we assumed exist, be the real number S. Now, if we're going to do integration by parts, then something has to be an integral of a derivative times something else, and there is a derivative here, rather a finite difference, because yk can therefore be written as sk minus 1. And that's true even when k is equal to 1 because of this convention. Therefore, the sum of the xk's up to n, which is the sum of bk times yk, by definition, is the sum of bk times sk minus 1, which I'll write as the difference of two sums, and re-index the second sum so that I can compare the sk's. Well, these two sums go over different indexing sets, but we can start both of them at k equals 0 since S0 is 0, and so there's just one term missing when I try to combine them, and that's bn times Sn. Okay, so here we have a nice expression for the sum xk, which once again looks like we've done integration by parts. And now it's nicely set up to divide by bn, so the sum we're interested in showing goes to 0. 1 over bn times the sum up to n of xk is Sn minus 1 over bn times the sum of bk plus 1 minus bk times sk. And now what I'm going to do is introduce s, so that is I'm going to replace sk by s in this sum, which means that I then have to add back in the same thing with an s minus sk. And so Rn is 1 over bn times the sum k going from 1 up to n minus 1 of bk plus 1 minus bk s minus sk. Now let's make a quick observation here. S minus sk being the difference between the limit of the Sn's and sk is the sum j going from k plus 1 up to infinity of yj. Our assumption is that the sum of all of them is finite, which means that the sum of a tail goes to 0. So s minus sk tends to 0 as k goes to infinity. Now that's going to help us immediately, because notice that by taking the constant s outside this sum, the inside sum here is a telescoping series, and the sum simply adds up to bn minus b1. So these initial terms give us Sn minus 1 minus b1 over bn times s plus Rn. Now, our assumption is that bn tends to infinity, and therefore b1 over bn tends to 0. And since s minus Sn tends to 0, in order to prove the desired conclusion that this tends to 0, it suffices to show that this remainder term, Rn, goes to 0. Well, to begin, let's show that Rn is a bounded sequence. Since s minus sk goes to 0, the sequence s minus sk is bounded by some m, and so this is less than or equal to m over bn times the sum, again, of the same telescoping series, which gives us m times 1 minus b1 over bn, and that's less than or equal to m. Now that's useful because if we look at the limit of the remainder term Rn, we'll use the same intuition that we've appealed to many times in the last few lectures, and write that as the limit as n goes to infinity of 1 over bn times the sum k going from some capital N up to n of bk plus 1 minus bk times s minus sk in absolute value. Why is that? Because the difference between this sum and this one is the sum of the first n minus 1 terms of this divided by bn. But each of those n minus 1 terms is less than or equal to some uniform bound m, and so the sum of n minus 1 of them divided by b little n, which goes off to infinity, just goes to 0. So we can choose whatever capital N we like to evaluate this limit as such. But now, noting that s minus sk goes to 0, we can choose n large enough that this is very small. In other words, this is less than or equal to the limit as n goes to infinity of the supremum, k bigger than or equal to capital N of s minus sk, times 1 over bn times the same telescoping series one more time. That once again gives us 1 minus b1 over bn. And now, as capital N goes to infinity, this stays bounded, and so we get that this limit is bounded by this supremum for any chosen capital N. Since we can make that as small as we like, it follows that this limit is equal to 0, and that concludes the proof of Kronecker's lemma. Kronecker's lemma is a handy little tool in real analysis. We're going to use it again several times in this lecture in complicated and simple ways, and maybe you'll find it useful in your daily life as well. But now we finally have all the tools in place to complete the proof of Kolmogorov's strong law of large numbers. Just to remind you, the statement of the theorem is that if xn is a sequence of IID integrable random variables with common mean alpha, and Sn is the partial sum of the first n of those random variables, then the empirical average, Sn over n, converges almost surely to the common mean alpha. These random normalized sums concentrate almost surely on their common mean. We already showed that it's sufficient to reduce to the case where we replace the sum Sn of the random variables with this modified sum of cutoff random variables. That is, we cut off the jth random variable at height j. And that's because this sequence and the original sequence were tail equivalent. A benefit of doing that is we've replaced xn with a bounded random variable, which is therefore L2. And so we can use, for example, Kolmogorov's convergence criterion, which we proved in the last lecture. That is, if I take any sequence yn of independent L2 random variables, whose sum of variances is finite, then the sum of the centered versions of those random variables converges almost surely. We're going to apply this with yn equal to the cutoff xn divided by n. We will conclude that this sum is almost surely finite, and then we'll apply Kronecker's lemma to conclude that this sum converges to 0 after centering, which is what we need. So we just need to check that the sum of the variances of those is finite. Well, the variance is a quadratic function, so we can pull the 1 over n out to get a 1 over n squared. And let's just bound the variance above by the second moment. Now, by definition, xn prime is xn times this cutoff with respect to xn. And now we use the fact that all the xn's are identically distributed, so we can replace the n with 1 here. To be clear, we can't replace that n. We're just observing that this quantity is a function of the distribution of the random variable, which doesn't change with n. So this sum of variances, now pulling the expected value outside the sum, which we can do by Tonelli's theorem, is equal to the expected value of x1 squared times the sum, n going from 1 up to infinity, of 1 over n squared times the indicator of the set where the random variable x1 is less than or equal to n in absolute value. How do we estimate that? We want to show that that's finite. Well, notice that this is a function of x1. And what function is it? Well, it's x squared times this function of the absolute value of x1. What is this function? This is just the sum of the series 1 over n squared, but where we start with n bigger than or equal to x. How do we do that? So first of all, we can see that this is finite, but we also have this x1 squared out there. Now remember, x1 is just in L1. We've now removed the cutoff. It's all over here. So we can't just bound this by this. That will not be finite. Instead, we have to see that this, as a function of x, is small as x grows, small enough to compensate for the potential non-integrability of that. Well, in order to estimate that, we can just draw a nice picture here and say, look, what we're doing is adding up the areas of these rectangles, but only starting at the rectangle which is past x, wherever x is. So let's write that as a function like this. This function of t is the function which puts a rectangle of width 1 and height 1 over n squared on the interval from n up to n plus 1. And I want to add up the areas of all of those rectangles, but only beyond x. So I can do that by integrating this function from x up to infinity. Well, that actually gives me an overestimate, because if x is, say, here, then what this integral calculates is the area of all of this, when in fact we only want the area of all of this, excluding this little bit. But that's okay, an upper bound will be fine for us here. Now that's useful because for fixed t, this function we're integrating inside here is nothing other than 1 over the floor of t squared. And the floor of t is bigger than or equal to t minus 1, so this is less than or equal to 1 over t minus 1 squared. And so this integral is less than or equal to the integral from x up to infinity of 1 over t minus 1 squared, which is a problem that you can give to your calculus students. It gives 1 over x minus 1. And just to compare to something else we're going to see in one moment, this is less than or equal to 2 over x. This looks like it would be problematic if x is less than 1, and in fact it is problematic if x is less than 1 because we haven't even defined the function for x less than 1. So all of this is only for x bigger than 1, as stated here. What about when x is less than 1? Well, if x is less than or equal to 1, then this is just the full sum, n going from 1 up to infinity of 1 over n squared, which has an exact value of pi squared over 6, which is about 1.645, which is less than or equal to 2. And so if I put those two together, what we get is that this whole term is less than or equal to the minimum of 2 and 2 over x. That's great, because that tells us that this expected value is less than or equal to the expected value of x1 squared times the minimum of 2 and 2 over absolute value of x1. And that means that this, in total, is always less than or equal to twice the expected value of the absolute value of x1. It doesn't require x1 to be square integrable. This is finite because x1 is integrable. Thus, the sum of the variances here is finite, and so by Kolmogorov's convergence criterion, this sum converges almost surely. That's almost what we want to prove. We want to prove convergence to 0 of this sum, but with the n on the outside, and that's where Kronecker is going to come in handy. So we can now conclude from Kronecker's lemma that this sum goes to 0, 1 over n times the sum of the centered versions of the xk primes. So let's write out what this sum is. We can break up the terms as follows. Now this is Sn prime over n, and remember that our goal is to show that that converges to alpha almost surely. And so, since this minus that converges to 0 almost surely, we are left to show that this converges to alpha almost surely. Well, again, let's note that the terms inside this sum are all determined by the distribution of xk, which is independent of k, and so we have the sum of the expected value of x1 times the cutoff of x1 by k. And now we note that all of these functions inside here, as k varies, are dominated in absolute value by the absolute value of x1, which is in L1. And so, by the dominated convergence theorem, and the fact that as I remove the k cutoff, I get almost sure convergence to x1 inside, each of those terms, expected value of x1 times the cutoff, converges to the expected value of x1, which is alpha, by the dominated convergence theorem. So what I have is just this sequence of numbers, alpha k, that converges to alpha as k goes to infinity. And what I'd like to look at is the limit as n goes to infinity of 1 over n times the sum, k going from 1 up to n, of alpha k. And it is a simple exercise at the level of undergraduate real analysis to show that this implies that that is also alpha, which finally concludes the proof of the strong law of large numbers. Now, before we turn to other pursuits, we have this nice theorem that tells us that a renormalized sum always converges almost surely to a constant. The question then is, okay, how fast does it converge? So let's talk a little bit about rates of convergence. So what we've proved is that the renormalized sum Sn over n minus the common mean alpha converges to 0 almost surely, which means that it is little o of 1. But is that the best we can do? Could it be faster than little o of 1? In other words, can I find some growing sequence an so that even multiplying this sequence, which converges to 0, by an, I still get something that doesn't blow up? Well, in general, if we're only making the minimal assumption that the random variables are in L1, the answer is no, you can't find a uniform better bound than that. Although that's a bit of a delicate question. But in real life, we're rarely faced with only L1 functions. Usually the functions are more integrable than that. So I wanted to highlight two theorems in that direction before we sign off on this. The first is a nice generalization due to Marcinkiewicz and Zygmunt, which says that if I assume that my random variables are in LP for some p strictly greater than 1 but less than 2, then we actually get this, Sn minus n alpha divided by not just n, but n to the 1 over p converges to 0. Notice that we can write this as Sn over n minus alpha times n to the 1 minus 1 over p. And if p is bigger than 1, then this is an unbounded growing function of n. And so what this tells us is that in this setting, Sn over n minus alpha is little o of 1 over n to the 1 minus 1 over p. Let me just note that in order to prove this, the method that they use is to follow the exact same proof that we just went through over the last 2.5 lectures. but with some trivial modifications. At the beginning, instead of cutting off xn by n, you cut off xn by n to the 1 over p. The same argument we gave that gives a tail equivalent sequence works here because of the assumption that the xn's are in LP. You'll find that the sum of the probability that xn prime doesn't equal x is bounded by the LP norm to the pth power of xn. And so we proceed through the proof word for word until we get to what we did on this slide here. And the only thing that matters is that we're now going to be dealing with 1 over n to the 2 over p instead of 1 over n squared, with n bigger than or equal to x. But if we do an analysis that's not very different than what we did here, we'll find that that sum is bounded by this function of x. Remember, in the p equals 1 case, what we got was 1 over x minus 1. And this is a nice finite bound that's good enough to push the proof through exactly the way we did on the last few slides. But note that there's no way to extend this estimate beyond p less than 2. This just blows up. And there is a phase transition that actually happens at p equals 2. So here we get a nice optimal family of rates of convergence here that depend on the integrability factor p. But once we get to p equal 2 and beyond, a new regime in the rate of convergence takes over. So let's start by looking at the case p equals 2. So here is a theorem that we are nicely set up to prove. In fact, this is much easier to prove than the L1 strong law of large numbers. Suppose that the xn are independent. We don't need to assume they're identically distributed. And L2 random variables. Suppose they have common mean alpha. And suppose they have uniformly bounded variance. It doesn't even need to be constant for this statement. If we take the partial sum, as usual, of the first n terms, and if Bn is any sequence of positive real numbers that goes to infinity fast enough that the sum of 1 over Bn squared is finite, then renormalizing Sn minus n times the mean by 1 over Bn converges to 0 almost surely, and in L2. This is very quick to prove given the tools that we already have. We're going to use the Kolmogorov convergence criterion and Kronecker's lemma. Here we're interested in Sn over Bn, but instead, looking toward Kronecker, we're going to consider the sequence Xn over Bn and look at its sum of variances. Well, that's just less than or equal to the sum n going from 1 up to infinity of 1 over Bn squared times the variance of Xn, but the variance of Xn is uniformly bounded, and so this will be less than or equal to that uniform bound, s squared, times the sum of the 1 over Bn squareds, which we assumed to be finite. And therefore, by Kolmogorov's convergence criterion, the sum of the centered versions of Xn over Bn converges and exists as a limit in the real line almost surely. And therefore, by Kronecker's lemma, the renormalized sum 1 over Bn times the centered version of Xn converges to 0 almost surely. So that's exactly what we needed right here, at least in terms of the almost sure convergence. For the L2 convergence, we can just calculate directly that the L2 norm of that function Sn minus n alpha over Bn squared is, by definition, the expected value of the square. That is 1 over Bn squared times the variance of Sn, but the Sn's are independent, and therefore the variance of the sum is the sum of the variances. The variances are all bounded by s squared, and so this is less than or equal to s squared times 1 over Bn squared times n, which I'm going to write as the sum, k going from 1 up to n, of 1. Now, we assumed that the sum of 1 over Bn squared is finite, and therefore, by Kronecker's lemma in this very simple context, this sum goes to 0. And that gives us the L2 convergence as well. So, the moral of the story here is that if you have L2 random variables, the rate of convergence is at least as good as n over Bn, where Bn is any increasing sequence of real numbers such that the sum of the reciprocal squares is finite. For example, we could take Bn equal to n to the p for any p bigger than 1/2. And that will get us here any polynomial rate of decay that is slower than 1 over the square root of n, just like we saw on the last slide. But we could do even better than that. If you look in the exercises of Baby Rudin, you'll see a good example of a function that is close to the border between summable and non-summable, is to take bn equal to the square root of n times the natural logarithm of n to the 1/2 plus epsilon for any epsilon greater than 0. You can't take epsilon equal to 0, then the sum of the squares is not finite. But for any epsilon greater than 0, the sum of the reciprocal squares of this is finite, and so we can get a rate here that's like log n to the 1/2 over root n, or a little bit slower than that. Well, it turns out that that is pretty darn close to the absolute best that you can ever do, because of the following strangely named theorem, the law of the iterated logarithm. This theorem, due to Khinchin, another famous K mathematician, states that if xn is a sequence of independent L2 random variables with common mean, and this time we'll assume common variance s squared, but again, we don't need them to be identically distributed. And if Sn is the usual sum of the first n terms, then Sn minus n alpha divided by this function, the square root of 2s times n times the log of n, does not go to 0. It also doesn't blow up. Its lim sup is exactly 1, almost surely. And actually, it turns out that the negative of this also has lim sup 1. So the lim inf of this sequence is -1. It doesn't converge, but it stays bounded between -1 and 1. That is a very precise statement of the exact rate of convergence here. What it says is that in this case, when the xn are in L2 or better, Sn minus n alpha over n is big O of the square root of log n divided by n. And that's the best we can possibly do. We're not going to prove this right now. It's going to be quite some time before we have the tools to prove this, but it will be one of the main theorems of this course. It will come after we make a dedicated study of stochastic processes, and in particular, generalize such sums to a continuous version called Brownian motion. But before we randomly walk off toward results like that, let's spend a few minutes next time talking about changing light bulbs.